So if P is coming down, okay, and then at point D, if you say that it's coming down, dy is coming down, what will happen to the structure? Anyone? It will start to rotate. Yeah, it will start to rotate. So the only correct answer in your dy, right? So we know that this is wrong, is that it has to be going up. So in this context, you will have the confidence to see, okay, or to assume what is the correct answer or assumption make for your free body diagram. Are we clear? Okay, it's not a guessing game, but sometimes it can be guessing. Okay, sometimes. Okay, not always. But if you were to guess, okay, if you were to be not sure, don't not sure with a lot of points. Just not sure with 1 point is okay. It's okay to just 1 point. I'm not sure whether is it going up or I'm not sure is it coming down. It's okay. Okay, but not point B, I'm not sure. Point D, I'm not sure. Then okay, let's back up. Don't start this problem, and then you are stressed. Okay, don't do that. Okay, so I'm giving you a condition how to analyze or how to construct your free body diagram, and most important of all, construct your free body diagram with confidence. Okay, not like I'm not sure. Okay, right. So number one, find the reaction forces at point B and D. Okay, we done that already. So the next thing that we're going to do, okay, the next thing we're going to do is the second thing we're going to do, okay, is to identify, okay, the operating range, okay, the operating range, or identify the limits, okay, in terms of distance. Today I can't write. To find the shear force and bending moment relationship. Okay. Luis Sanchez, shear. Oh, it's hinge only one on one side. Now, Luis, there's always shear in this beam. Okay, there's only a few specific point where the shearing force is equal to 0. Okay, and for this case, okay, as I said, when selecting the beams, we only go to focus on bending moment. Okay, why is that? Because I've not taught you how to combine the shear stress and bending moment using Mohs circle. Okay, I've not done that yet. So that's why we are just going to focus on bending moment. Okay. Okay, what do I mean by identify the limits in terms of distance to find the shear force and bending moment relationship? What do I mean? So we usually create a table for this, okay, points. So what points to take, okay? The points will induce a limit, okay? So let's consider the points. So the points to consider is at point A. Then we are going to do point A to point B, right? And then we're going to look at just point B. And then we're going to look at point B to point C. And we're just going to look at point C. And then we're going to consider point C to point D. And finally, we are going to look at point D. Okay. So if you look at the number of points of or I'll say range to find your shear force and bending moment relationship. So how many points are there? Okay. Or how many equations we're going to form? 1, 2, 3, 4, 5, 6, 7. There's 8 locations. Okay. But more important, you have to, next thing, you have to identify the limits. Okay, you have to identify the limits. So the limits, what I mean by limits over here is in terms of what? Distance. Okay, it's in terms of distance. So what do I mean by in terms of distance? Okay, so in terms of distance, it's in terms of what? Limits. So A at point A, x is equal to 0. Oh, wait, let me get the distance first, and I'll ask you why the datum is on the left hand side. Okay, so from A to B is 0, x go to 0.8. At point B, x is equal to 0.8. B to C, so B to C is 0.8, x to 3.2. At point C, x is equal to 3.2. At C to D is 3.2, x, and it goes up to 2.4, 4. And over here, x is equal to 4. Okay, so we are going to form the equation, right? So I'm going to draw two. Right, so we're going to generate a table like this. So this is V as a function of x, M has a function of x. Okay, so all these will all be your equations. Okay, but I want to make you take note. Okay, I'm going to write this down. Okay, A is going to be a constant. A to B is going to be an equation. B is a constant. B to C is going to be an equation. C is a constant. Now, can you see the trend? Yes or no? C to D is an equation. Now, when is it an equation and when is it a constant? Can anyone tell me?
It's an equation when it has a range.
Yes. Okay. Well done. Okay. A thing about engineers, okay, is we have to look at the trend. If you have a range, right, you have a what? Equation. And if you have a constant limit, right, means the shear force and bending moment is going to be absolute, right? Then it's going to be what? Constant. Okay, this you have to observe. Okay, now question for all of you: why is the geometric datum always on the left hand side? Anyone? And is I won't call it common sense. Is you have to link with math, then you will know why it's always on the left hand side. When I say datum on the left hand side, when we select our variable, right, it will always, variable x is always at that direction. Any idea why? Anyone, please?
If A is 0, going to the right would be positive.
Yeah, but why it has to be on the left hand side? Why I cannot put the datum at point D?
Because all your values would be negative.
The values will be negative. Jenna, you're partly right. Okay, this is because when we construct our shear force and bending moment diagram, so it can be a shear force or bending moment diagram. So the purpose is what? We're going to construct a shear force and bending moment diagram, and it's always known that on the left hand side is always going to be 0. So the datum shall not move at all. I repeat, the datum shall not move at all. Okay, so we're going to construct. I'm not saying that this is how it looks like. We are going to construct shear force like this, for example. Okay, this is your shear force. Okay, and then your bending moment is going to look like this. Okay, so this is why, right? This is y, so this is for your moment. This is just a sketch, okay? It does not mean that this is a solution. And this is shear force. So our geometric datum is always on the what? Left-hand side. And based on convention, okay, positive is always going towards the right, okay? You can also take on the right-hand side, like what Jenna has mentioned, but then your distance will all be negative, okay? And I don't know. I want to see positive, okay? You can do that. I'm not saying that you can't. You can. The answer should be the same, but you need to be able to what? Flip things around, okay? So now, most important thing about identifying the points or the limits, okay, is at every point, okay, you need to find what are the values. Okay, like point C, you also have to have one for point C and point D. Sometimes if we don't label that this is point C, okay, you have to know that that is a change. Okay, so you have to know that you have to find the constant at point C. Okay, and then the range is whatever that is in between. So these are the range, these are the range, and these are the what? These are range. Okay, so this is how to identify the points. So once you have identified the points, okay, then you can start forming your equation. Okay, then you can start forming your equation. Okay, so we are going to start forming the equation at point A. Okay, and point A is like pretty straightforward. Okay, is one of the most easiest one. Okay, so let's look at point A. So at point A, right, at point A, right, and then you write down your x is equal to 0. Okay, so when x is equal to 0, right, I'm going to draw. So this is very small. Okay, this is a very narrow what do you call narrow section. Okay, so it's equal to 0. So when over here, so what we're going to do now is we're going to put in the equation or the distributed load. So over here, you know that so the datum's on the left hand side. This is x, and we declare x equal to 0. You have equivalent load coming down. Equivalent is 50 times 10 to the power 3 multiplied by 0. Okay, so our analysis, okay, so our analysis will be in this direction. Okay, analysis direction. So then later on I'll explain why this is down. Okay, so this is equal to V, and this is our point A, right? V at point A and the moment at point A. So we know that the equivalent load is 50 times 10 to the power 3 multiplied by 0. There's no distance. Okay, so what we're going to do is we're going to carry out a static analysis. From left to right. Okay, so we do summation about forces in the y direction is equal to 0. So we know that 50 times 10 to the power 3 times by 0, okay, minus V at point A is equal to 0. So we know that V at point A is equal to 0. Okay. Then we have anti-clockwise. So I mentioned about moment Z at a distance 0. Right. So for this case, we know that 50 times, so this is going anti-clockwise, 50 times 10 to the power 3 multiplied by 0 plus by m at point A is equal to 0. So we know that m at point A is equal to 0. Okay, so once you have that, immediately from here you put down Vx is equal to 0, or m and mx is equal to 0. Now, the thing now is this, okay? Y, this direction. Y shear force is equal downwards, and moment at point A is